So today what we're going to do is we're going to talk about AI and C++. And I've got two workshops that I'm going to be doing, one called AI++ 101 and the other called AI++ 201. And the difference between them is that 101 is kind of like a basic, kind of like when you were in school and you needed to know what a compiler did. There are a number of people that contend that if you don't know how compiler construction works, then you don't know how computers work. That it's so fundamental to understanding. And I just know that for me, understanding the raw basics of how things work helps me utilize them better. I know that we'll get into my story here in a little bit, that I couldn't really see any benefit from the use of AI with C++ until I understood more of the details. And then and that's what we're going to do in 101. We're basically going to build a coding assistant. Think Claude Code. We're going to build Claude Code in C++. But I mean, it's not going to be so full featured. It'll be a toy, but it'll be something that we can actually play. And I'll actually demo it here in a little bit. The other one, AI++ 201, is kind of like it's not the next semester class. It's not 102, but think of it more like a data structures class compared to a beginning programming class. But in there, we're going to talk specifically about how to leverage tools and utilities in order to get the best out of C++ with AI. AI code gen can be really difficult with C++. And there are a few things that they probably apply to other languages. They probably apply to other paradigms. But since those aren't my paradigms, these are things I've figured out that I needed to do specifically for C++. C++ has some unique characteristics. And we'll talk a little bit about that as we go along. The one thing to note is that the workshop is being recorded. And what I want to do is I want to have as much participation as possible. And so along with that, I want to encourage you that if you have any questions, to go ahead and just interrupt and answer. So your microphones are left on. So if you would just make sure that you mute yourself, but if you want to speak, if you want to ask a question, if you want to do any, then please interrupt. That's what this is for. I'm not going to hold questions until the end. Just open up your mic and shout your question. If for some reason I didn't hear it or you don't think it was heard, then you can also enter into the Q&A. If you do ask a question, then that will be part of the live stream and it will be part of the recording. So make sure that you're okay with your voice being on the recording if you just ask a question yourself. If you want to ask a question but you don't want to be on the recording, please feel free to just type it into the Q&A and I'll be able to see it and we'll be able to go on from there. Okay? All right. So I'm going to stop sharing this and I'm going to share a different screen. Just because I've got a different set of things to go through. And in the end, what we're all going to be doing today is playing. This is actually what I think the actual workshop is like. And I want to say that this workshop I've done as a trial run several weeks ago with a whole bunch of people. And then I also have done another version of it just a couple of weeks ago. And so I've gotten a lot of feedback. And so I've been able to improve some of the content, but actually not really the content, just how it's been delivered. The biggest problems that we had were that people didn't actually have the code that they were going to work on. That's not a problem for you today because we're not going to be working on the code in labs. But I want you to understand that the actual lab or the workshop for both of these, half or more than half of the time will be spent in labs where we're working on code, we're working with the AI, we're working on code generation. And we're not going to have any lab time today. I wasn't sure exactly how that would work out. But the other one of the comments that I got about the AI 101 was there were some people that responded that the very first stuff we talked about was the best stuff they had all day, and it changed their mind completely on how to see and understand how the models work, which was one of the points. There were an equal number of people that responded and said that that content could be cut out because they didn't really need it. And so it's one of those things where it was most important for some and not for others. And then also people still wanted more time for labs. So today what I'm going to do, it's a taster, but it's more than just a taster. The beginning part of what we're going to do, a portion of it is just me commenting on AI and answering questions generally on AI with C++. But the rest of it is actually basically a part of the workshop that I'm going to pull out because I'm going to send people a link to this video and have them watch this instead. So I want to explain why these workshops are important to me. And again, please interrupt me at any point in time with any questions, comments. That's it. It's hard when we're this remote thing. Normally when I've done workshops like this before, it's all been in person. And so I could actually see people. Well, I can't see anybody and I can't see anything. So just please reach out to me if you have a question. But I'm going to probably philosophize a little bit more than I thought. I was driving home from Atlanta yesterday, and I thought that that since I've got time in this particular setting, it's worth me explaining my background a little bit more. Because my journey in AI didn't start last year. My journey in AI actually started back in 1986. In 1986, when I wrote my first code in college for using AI. And then I went to grad school specifically to get a PhD in AI at Vanderbilt University in Nashville, Tennessee. And while I was there as a graduate research assistant working on several projects that were funded. My research professor was awesome. He did lots of stuff. I worked specifically on an expert system that was trying to help an oil consortium figure out where they were supposed to drill for oil. So it was doing prediction on where you should drill for oil, which is something that's important to the AI that we're doing today. Back then, a lot of the stuff you had to try and do what we call qualitative reasoning, because quantitative reasoning required a lot of compute. And there just wasn't as much compute. There were a whole lot more ideas than compute, which is why during the next course of the next year, I was part of 7 publications that were published in academic journals and in 2 of the artificial intelligence conferences, ICHI and AAAI. We worked on qualitative simulation stuff that was for FedEx, and at the time back then was the space station research. So my background with AI goes all the way back to that point in time. But in the 80s, we had what we called an AI winter, which ironically people are talking about now. They're talking about the bubble crash, which there was an AI winter in the 70s and there was another in the 80s. And I'm sure there probably will be an equivalent one here coming up soon in somebody's estimation. But what that meant was there were lots of money pumped in to AI research, and and there wasn't a whole lot of jobs. And I decided I wanted to solve problems, not necessarily write about them. So obviously with all this experience, my first job was writing Unix kernel code. And so I got into the systems level with C++. But the reason that this is important for what we're talking about today is I almost never got a degree in computer science at all. In 1984, I was having to write Pascal code because my math instructor told me that I had to take 2 computer programming classes. and I was failing that class miserably. The thing that changed my life there, and I guess it changed my life because it changed the course of the next 45 years of my life, and that's that, or 40 years, I guess, since it was 84. The three-line swap. I couldn't figure out how if you said A equals B and B equals C, that A and C didn't equal each other. And a buddy of mine sat down and spent 45 minutes explaining to me the three-line swap, and it took a long time. But I finally understood that these were just labels to memory locations. And if I could just move things around, then I could understand what was going on. A light went on, and I really didn't struggle with much at all, which is similar to what happened last year. If you guys were at CPPCon last year, there were about 5 or 6 talks on AI. There was a cranky old man that stood up after every single one of them and asked the same question. He said, okay, so this is great. How do you get AI to not generate crappy C++ code? And the answers were somewhat different most of the time. But the thing in one of them, and I was going to pull the clip, but it hadn't been shown yet. In one of those last year at CPBCon, there was a panel. I can still see it. I think Imbal, who just got done speaking, was on the panel, and I think Jason was on the panel, as was Matt and Daisy. There were a couple of other people on the panel, but Daisy looked at me and asked what was my mechanism. And I explained what I was doing. I had been taking prompts and running them through shell scripts and sending them to the model through the OpenRouter API and getting back responses and running them through a compiler and taking the compiler errors and sending them back to the model and taking those and coming back and forth, working on trying to get a piece of code that would compile. And then if it would try and run the tests. And if it ever did succeed, it was just a bunch of garbage. And I didn't understand why. And the breakthrough for me was what Daisy told me last September. It's only been just since last September. Daisy said, the problem is you're 6 months behind. And I didn't understand what that meant. And the thing was that I had been working on the same problem. You guys are familiar with the C compiler thing, right? With pop up some stuff, little shooty things or whatever. Are you familiar with the C compiler thing that Anthropic said that they built? There was a lot of contention online with people either pushing hype about this was the greatest thing since sliced bread, or people saying that this was just a load of crap, that it couldn't even compile Hello World. And I think everybody missed the important thing that was important to me, because what this person described was exactly what I went through. And it's why I'm talking about this today, is because I want you to understand where I'm coming from. I'm not preaching AI. I'm telling you my story. I can't make a big produced movie. I'm not a great speaker. All I know is my experience. And 2 years ago, when I first started playing with the Gen AI, I had one goal. I came up with the litmus test. My background has been in the trading space since the 90s. My one goal, I wanted to take specifications and a document that me as an expert could describe what feed handlers are, and I wanted to take the NASDAQ specification for the NASDAQ feeds, or the Oprah specification for the Oprah feeds, or the New York Stock Exchange specification for their feeds. And I wanted to be able to have AI generate a C++ feed handler that would work. Ultimately, I want it to generate one that is indistinguishable from my own code. But the first thing I wanted to do was just have it generate this, and it couldn't. But the breakthrough was for me understanding these 4 pillars. And this is why I'm going to this basics. I'm spending this time in this talk going through this, because I think if you want to, my opinion is, if someone wants to do generative AI with C++, you have to understand these 4 pillars, or you're never going to make progress. You're going to keep doing the same things that everybody else keeps doing, and you keep getting the same crap that I was getting. And the first thing is the models. We have to understand what they are, why they generate what they do. How do they generate text? Why can you have a meme where a model says stupid things that flood on the internet? Why will a model tell me that all the tests are done when they're not? Why will a model just outright lie to me? Why will it write bad code? We have to understand how the models are so that we can understand it, so that it's not just a joke or frustration. The second thing is we have to understand what prompts are. Prompts are not, hey, write me a feed handler. That's not a prompt. I mean, it is a prompt, and some people try to do it, but we have to understand what the prompts are. The third thing to understand is the third fundamental pillar is context. What is it? It's not just a big array of bytes that we can just fill. Why is it that when the context gets bigger, the production gets worse? How can we manage this context? And the fourth thing is tools. How do the models interact with tools? I actually understood the first three before last September. I understood the models and the prompts and context very well before last September. The thing I didn't understand was the tools, because I had basically been out. I had a lot of things going on in life, and I really wasn't following it that much until September. And once I understood what the tools were, I understood everything, why models matter. And so the reason that the fundamentals are important for us is that when we were in university, you wrote a compiler probably. You didn't write a real compiler. You wrote a toy compiler. But all this time later, you understand how compilers work. You understand how computers work. You are better at writing code because you understand how compilers work, especially C++, because C++ is close to the compiler. I mean, if you go to most talks, you're going to see the C++ running on generates assembly, where you know what not only what the compiler is doing, but you depend on what the optimizer is doing. I don't think it's any different when it comes to these language models. When it comes to writing code with AI, I think you need to understand the fundamentals. You need to understand the basics. It's even more important, I think, with C++. My goal at the end, when you get to the end of this whole workshop, my goal is that you look back and you go, man, that was a whole lot of fun. Is that really all there is to it? Like I did when I looked at my 3-line swap. Is that all there is to it? So I spent a lot of time here because I've received a lot of flack online from other people. I've received people have told me if I didn't know you, I wouldn't believe what you're telling me about AI. And that's okay. I'm not trying to say it's the greatest thing, but I do think that it's important to understand these fundamentals. What are these fundamentals? The first thing is that what LLMs actually do. And this is kind of the first thing that we would actually be doing in the class. And I'm going to do it here with you. LLMs are trained to predict the next token. And that's it. I mean, that's pretty much what. Now, I'm going to talk to you a lot about how models work. I'm getting ready to. But I'm getting ready to steal a line from Scott Myers when he talked in 2014 about universal references. He said, what I'm about to tell you is a lie, but it's a convenient lie. And what I'm about to tell you about LLMs, it's a lie, but it's a convenient lie, because to tell you everything would take hours, right? And we don't have that. We don't have that luxury here. I will say that there are some great visualization tools. If you go to YouTube and look up the videos on transformers, that 3 blue, 1 brown, Grant Sanderson, those are great videos to tell you how the math actually works and to visualize how these things are presented. But what is a token? A token is not a word. A token is probably part of a word. It's punctuation, white space. But everything that a model generates is tokens. You hear all this, token burn and how much your tokens cost. Well, the communication mechanism, the medium of communicating with a model, is what we call tokens. And if we look here, it says the capital of South Carolina is, and I broke everything. I broke a word up into tokens just because I didn't want to get into the nitty gritty of how they break up. Partly because every model defines its own token. The model defines what is a token for it, and it has to, because that's how it gets trained. And then all we're going to do is predict what is the next token. And so, what do LLMs actually do? What do tokens look like? How are tokens broken up? How are they used? And here's 3 links that I'm going to actually pull up, and what we're going to do is we're going to play with them. In the class, I would basically have people, I would give questions about these, and I would demo them and then let people do the exploring themselves. But we're not going to do the exploring themselves. What we're going to do is we're just going to go through it together. So when I pull these websites up, I want you to ask me questions. If you want to experiment with something, ask me and I'll experiment with it into the thing. But hopefully through these links, we're going to get an idea of what these models look like. And so the first, oops, let me click back on share. So the first thing we're going to look at, I actually ran a test of this morning, which is good, because the previous link that I've been using in the previous times I've done this, it apparently is no longer a link. There was a squatter on that site now, so I had to go find another one, which is fine. Which is why I'm using OpenAI's. I didn't want to show examples that were wedded to a particular company or a particular model, but that's why I'm using this OpenAI platform right now, is because the previous link is just dead now. But what we see here is this is all about what are tokens. And if we just look here, I typed in this text, and for a few reasons. Okay, you can actually see, if you look down here at the bottom, I'm going to change. These are GPT token models, and you can see that they actually change, right? Even the number of tokens. So from the legacy tokens, this was 94 tokens, and then GPT-3.5 legacy, it's 72, and here it's still 72. Actually, these are pretty close between 5 and 01. But not only did different models have different ways of representing tokens, the models within these big labs do as well. So we see here that tokens are broken down, and tokens are just a representation. It's a fixed set. So when you sit down to train a model, you know exactly how many tokens you're going to represent. Because that's your whole entire workspace. It's your vocabulary. If, for example, you get something like blarg is probably not one of the tokens, especially for GPT-3 legacy, right? It's just not going to be one of the tokens. And so what they do is they take it and they break it down as many times as they need to until they can get a recognizable token. If they have to, they'll break it down to per byte, such that each token is a byte if they have to. So for example, consider like maybe you put in Unicode or something like that in there. And everything gets broken down into a token. The reason is because then this right here is just a big array, a vector of numbers. This is the same as this, just in tokens. Each one of these colored items is a token, and they get broken down into an array of numbers. The numbers each number represents a specific token. Note here, when we look at the example here, we've got at the bottom, we've got that blarg, then we've got Jody with a capital and a lowercase. So this is the first one, 411118. Okay, that's the capital J and then the OD. And then this one is the lowercase j and then the OD. OD being a token is kind of interesting. I don't know what that means, but I found it kind of funny. And so you can and then you can look here at the breakup of the C++ piece, right? This part right here is just a piece of C++. And we can see how those tokens are broken up. So you've got like the namespace, and then a colon together is a token. And then this left arrow, right? These are specific tokens. Int, pair. These are all just their own. These are broken up into recognizable tokens. If you see something that's broken up into multiple things, then that item itself is not recognized as a token in and of itself, and any of the math is going to have to at least come into play with multiple of these. Okay? Any questions on how this is done or why this is done? So this is how we go from words to tokens, or in our case, from code to tokens. All right. So why is this important? Because tokens is how we end up generating output. And one of the things that people ask is why do models invent things? Why do they hallucinate? And one of the things to understand is after you're done with in the next 10 minutes, your question isn't going to be why do models hallucinate? Your question is going to be why do they not ever or always hallucinate? Why do they ever get anything that's not a hallucination? So this right here, this is a transformer diagram. Transformers came about in 2017 from the Google people. And a transformer is just a construct of several different things. You've heard of neural networks, and a transformer is not, but it's composed. Parts of it are neural networks. But what we're going to do is we're going to just run through what this does. And again, the reason we're walking through this is because it's important to understand how these things work. You don't have to understand the math, just understand what's going on behind here. So this is an example with using GPT-2. It's a small model, but it's small enough for us to actually be able to see and work around. So the first thing we're going to do is if you go to this website, you can type anything you want in up here, right? So and then you click generate, and it will generate all the stuff on the left, right? So we see these embeddings. And any technology sufficiently advanced is imperceptible to magic, but this isn't magic. And I'm going to try to explain what some of this stuff does so that we understand how this works, because we're going to be working with tokens forever. So the first thing that happens is you end up with an embedding. And if you want, I'm going to follow this here. I'm not going to read it necessarily word for word, but I am going to walk along so you can go back through it later. These embeddings just turn letters into tokens. It turns words, text into tokens, so that you get text into some number. The reason they're numbers is because you need to do math with them. You need to do some type of identification with them. These transformer blocks, they basically mix this. There was a paper that Google came out in 2014 that, I think it said attention is all you need or something. This is basically doing the attention part of it. And we'll get into that a little bit. And then the end part is basically where we end up with these probabilities. And you just have a probability distribution. And so all you're doing is you're embedding text into numbers. You're taking these numbers and you're feeding them through this network of nodes and weights. And some math is going to be done on those numbers. And the result is going to pop over here on the right. If you look, that is going to be one probability likelihood for every single possible token, right? So if there's 30,000 tokens, then there will be 30,000 possibilities. If there's 1,000,000 tokens, there'll be 1,000,000 possibilities, right? So it's basically saying, given this vector of input, what is the probability that I get any specific one token? Because it's just predicting the very next token. It's not predicting a paragraph. It's not predicting a function. It's not predicting a test case. It's predicting the next token. And this is basically what this is doing. Remember, these are simplified. They're lies, but they're convenient lies. And so the first thing that happens is we do the embedding, which we've already talked about and we've experimented with. And then the next thing is that the token gets split out into a vector, right? So in this particular case, we see there's 50,257 tokens in the GPT-2 vocabulary. And and each one of them has a unique ID. And so this token embedding creates a vector. This vector is then used along with the positional encoding, like as you can see in the yellow column there. Is it in position 0 or 1 or 2? So you've got the token that each one of those tokens uses a lookup table to get a vector. And then that is combined with the positional coordinate of where it is in the text, what's its number in the text. And then this transformer block takes that array, that vector of numbers, and it does an attenuation on it. It basically tries to, it has this breakdown here, this QKV breakdown, which I think there's a screen here next that'll talk about it. And then it just sends it through an MLP and to basically a neural network to do this transformation. And so this self-attenuation part, this is the attention piece. It basically tries to help capture the meaning and relationship between these tokens. Even if they're very, very far apart, right? Because if you think about you're trying to map things on an XY axis, and if you have two words that are close together, then they're gonna be close within that XY plane. And so then there should be some relationship between those two tokens. Well, we're looking at here when we look at these models in a multi-dimensional space that you can't even fathom. The number of dimensions, you can't even fathom the number of dimensions. And so it's hard to imagine where things are location-wise, but that's what we're doing here. It breaks it up into this query, key, and value, and this really isn't that important what these things do. It's just that what they're doing is they're trying to figure out what types of weights and biases should be applied to this vector of numbers in order to more aptly map it and spread it out or bring it together when it sends it into the neural network that it's going to be sending it into next. And so after creating these values, basically you've got a smaller set of numbers that are then going to be sent in, and it's just a dot product. If you think of why you have to just be fast at matrix multiplication in order to do this, you'll see this term soft max. This is just what the soft max is doing is it's taking the value and it's trying to put it into a value of 0 to 1, which is going to be its probability. And one of the things that's interesting to note here is that after these scores are done, you've got a probability between 0 and 1 for every single one of them. And then you just rank them. There's this thing called temperature, which we actually play with in our coding example. When we do our code in the actual workshop, we will play with example, or we will implement temperature and see what it actually does. But think of temperature as a scaling factor. It's going to shrink or expand this mapping, right? So if things have a higher probability of occurring, then they're going to be much closer together, or they're going to be spread out, right? So if we look at this temperature here and we change it, see the probabilities here? You've got the scaled values as we change this temperature. See on the screen as we change this temperature? We change the temperature and make it smaller and smaller and smaller. Notice how there's now a much bigger difference between the ones that have a higher probability and the ones that have a lower probability. And then if we make this temperature very big, there's a much less there's much less disambiguation between these scaled values. So that's what temperature is doing. It's just a temperature of 0 is basically gonna just pick the one that has the highest probability, because the very next thing that happens after doing this is that there's a strategy to pick the next token. And so you're going to basically take the ones that are likely to be picked, and you're just going to do an RNG. You're going to randomly pick one of them out of the ones that are possible, right? You've got a random number generator that's generating your scale on your 0 to 1 probability. And again, remember, these are convenient lies. but it's just how is this done? And so even if something is the most likely outcome, it doesn't necessarily mean that that's going to be the one that's selected all the time. 0.7 is usually, like, if you're going to use open routers, 0.7 I think is what they use as their default. I've seen, and my testing kind of confirms it, that a value between 0.3 and 0.5 is probably better for doing code generation. It removes some of the variability without restricting it too much. So if you're actually going to be doing code generation, you probably want to be playing with this temperature value, and you need to understand what it's doing for the code that you're going to be creating. So this is basically how these things are picked up. Nobody stopped me. Anybody got any questions here? Okay, maybe I'm being too basic, but all right. So this next token of prediction visualization, this is where I would basically have we just play, right? So if you look here, never going to give you up, never going to let you. What's the next probable answer? And then we see what these tokens, the prediction of these tokens, right? Let's get rid of that. And as we can see, it's never going to give you up, never gonna. The words to the song are let. But we see here the thing that has the highest probability is give. Why do you think that is? Anybody?
We often say things twice.
Okay, yeah, we often say things twice. That's true. But plus, it's already there within our context. This is important. This is important for so when we're generating like C++ code, if you're generating code in a brand new directory where you've got nothing there, all it has to go on is the context that it's been trained on. If you're actually writing code in your current directory and you've got existing code, it's going to at some point be scanning that code for some reason. It'll be reading parts of those files, and that will be in the context. Just like here, where I'm never going to give you up, never gonna, it's going to probably tend toward give because it's seen that recently within its context. So you've got your training data. That big network that we talked about earlier, those values, those scores are set by the training data. Well, how is the training data done? It's basically, it's an average. It's an average of all of the data that it's seen. And then they go through several different phases of reinforcement learning, where in this reinforcement learning phase, they'll basically, there's companies that are hired to actually perform these types of services where they'll go through and use their model output, or even now what they do is they'll synthesize it. They'll say, hey, here's code, here's a prompt, how do we get back to it? And they'll create what they want as the path from a prompt to an endpoint, and they'll then train the models on those things so that it gets better at generating that kind of stuff. So if you can have some code available, so if you're starting with a very fresh directory with nothing in it, you're probably going to get better code gen if you at least give it another directory, a sample, say, hey, use this as reference, and point it to another directory that has code that you like or that you want it to imitate, rather than have it just go in a blank directory. If you don't give it anything in its context to use, it's just going to use what it was trained on. And I can guarantee you, if all you're going to do is get stuff that was trained on, you're going to end up with stuff that you don't like. That's where I was. End up with stuff that I don't like because it's like what it's trained on. And then it generates more of that. And then as it's loading your code into its context, it's just loading over and over the same stuff that it generated based on these average values. And so my tip for you, or one thing that we talk about in generating C++ with these models, is if you understand this principle of what it's seen, it's more likely, even though we all know that let is the thing that has to be, because that's what the words to the song are. The model doesn't know that, and it's seeing give right here, and so it's saying, hey, that never give you up. That makes sense. Never give. And it's got a very high probability. You want to make sure that when you're generating C++ code, that there's something within its context to help it know how you want it to generate code for you other than just what it was trained on. That's a very important thing to think of and remember when you're trying to generate code. It's not just that it tries to follow the leader of what you've got there. Oh, this guy likes this thing, I'm going to try and do it. It's that as it's been reading your files and trying to figure out what to do, the context has been loaded with these things, and that's going to dictate what gets predicted. Okay? So I would suggest you play with this a lot. I mean, really, type code in here. Go to this website and type code in here. I'll put links to this in the chat. But this is the link to this right here. Okay, but I would go here and play with this. The next one is similar, but this one's a little bit more. And this one actually explains what we just talked about a little more. So here's this whole value. If I start counting to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, you can see that this is a sequence progress. The element gets better at predicting the sequence, and by the end, it's 100% correct about how things are going to continue. The way to read this colorization is each one of these colorized things tells it how good is it at predicting what that token would have been. And up here, we can look, as we hover over each one of these things, we see the probability of each one of these coming into play. Okay, what was the probability that it was going to have? So right here, just given if its chance to predict and start is pretty small, right? But and so remember what we saw earlier is we're just predicting another token. And this is a thing to remember about when you giving context. You send it something, it has to basically go through and take your context and predict the next token, and then predicts the next one, and predict the next one, and predict the next one, and predict the next one. So if you're trying to build up a function of code, it's got to predict each one of those tokens. And every single time it predicts a token, it's got a probability that it's going to predict something that you don't want it to predict later. And so we can see how likely it is to predict. See, all these ones that are green, it's basically predicting the one that got generated. And this sentence here, the first time I write this sentence, the model is quite confused about what token is about to come next, right? Look in here. It's pretty confused. It doesn't know what's happening. But the next time that this sentence is there, it saw it immediately. And it's like, oh yeah, this is in my context. I'm going to try and imitate this. This is interesting, but for a C++ programmer, this is way more than interesting. This says, instead of just giving it a prompt and saying, I want something, I'm better off giving it a pattern, giving it code that is like what I want it to do. Give it a framework. If you're writing code that is similar to things you've done before, then give it the thing you've done before. If you're writing code that uses a framework, but it's just using it, even if it's using it in a different way, give it code that you wrote or somebody wrote that uses that framework, and just put it in its context. Say, hey, use this in your context as reference. And you don't even have to tell it to use it as reference. The fact we didn't tell it to use this sentence as reference, just the fact that it was in the context helped the model better predict what it was going to happen. This means that you're going to have less tool calls. You're going to have less possibility of getting things wrong or having to go into code review and getting your code reviews denied. Okay? So these are all cool things to play with. The big thing they do is they teach you how these models work. You don't have to know the math. You just have to understand that they're just predicting another token. Any questions on this? I probably just spent way too much time on it then, just harped on it. If nobody has questions, they probably already all knew it. Give me some feedback. Shoot me an email at Coach Hagins, coachhagins@gmail.com, if that's the case. Okay, so But that's why it's important for us as C++ programmers. So what do we have? What do we have next? So all that stuff that we just did, that was kind of like a lab that I would have people do on their own in groups, talking to people, figuring out how all this stuff works. But the big thing we need to know is that models don't know things. They just predict statistically likely continuations. And if they don't know things, then what happens? Well, one of the things for us to know is how do these conversations work? What's the difference between a chat bot and an agent? If you have your first AI conversation and you say, I'm working on a C++ project that processes sensor data from IoT devices, it knows what you're doing. And then when you say, what data structure would you recommend? It has to have previous information, right? It has to know what you're talking about. Because if you just gave the chatbot, what data structure would you recommend for buffering the readings? It would tell you, I have no idea what you're talking about. And then now you can tell it to show me the implementation. The thing to understand about context is the server does not have your context. Now, yes, OpenAI just last week, I think, released a WebSockets implementation that they're trying out with people, but that's just to reduce the amount of traffic going between the client and the server. What actually gets presented to the model is the whole entire conversation. And so when like OpenAI, all of the APIs that you have, you send the entire conversation. So in this case, if you send, I'm working on a C++ project that processes sensor data from IoT devices, it'll send back and say, hey, great, I know what that is. What do you want to do with it? The thinking models might even say, oh, you want me to write some code for you? And then it might even try to write code for you. But then if you tell it, what data structure would you recommend? When you send what data structure would you recommend for buffering the readings, what you do is you send the system prompt again. You send the original question, I'm working on a C++ project that processes sensor data. You send the response it sent you, and then you send also your next question. You're sending the entire array. Think of the conversation as a complete history of your conversation. And every single time you connect to the server, you send it the whole entire thing, and then that's it. Now, this is great for load balancing because they don't have to worry about where you were last time, who you were talking to last time, or whether that state is saved, because they can just send your next request to anybody. But it does mean that you have to be aware of your context because your context continues to grow. So models are stateless. There's no memory between API calls. Every single turn, you've got to send the entire conversation, and it looks like memory, but it's just a big replay machine. When you talk to the model, all you're doing is replaying the entire conversation. And then when you add, the next thing that you add is like, please explain this. You're going to send back all 50,000 tokens plus whatever tokens you had in please explain this. Okay? And so when we talk to models, there are three message roles. There's the system. The system prompt is basically what sets how things are looking. Basically, it sets the attitude and the tone. There's the human messenger's response, right? So there's the user request, and then there's the assistant. So when you talk back and forth, you're going to send the system prompt, and then a user prompt, and then you're going to get the assistance message. The next time, you're going to send the system, the user, the assistant, the user, the assistant. Okay? And so when you explore tokens and prompts, you'll figure this out really quickly. But the big thing that you need to understand when getting into C++ generation is that now that you know what's really going on, there's two things that are critical: context management and deterministic workflows. So in 101, what we do is we basically take all of that stuff and then we spend the whole rest of the day building Claude Code. I'm going to, we basically build Claude Code. I'm going to actually show you, I'm going to share my screen to show you the output of that. All right, I want you to pay attention to this one. I gave it a command. This is basically the program that we write in 101. This was the whole thing. I basically gave it a prompt to add a new feature. The new feature it was supposed to add is that it tracks usage across all tool calls. It got to the bottom and it said, hey, this was the message from the feature. This was the message from the model. Hey, feature usage traffic implemented successfully. New command, usage traffic provides turn-by-turn context traffic details, listing every conversation, currently one API call per turn within each turn, with prompt tokens, completion tokens, total tokens, turn tokens, and grand totals. And here's even an example of the output. But look what the previous message was. It doesn't even compile. And this was, it doesn't even compile. This wasn't what I would call a great coding model. This was basically Grok. It's not what I would call a great coding model. I was trying to find a model that would give me something stupid like this pretty easily, and it did. I just gave it a simple command. It completely failed. It wouldn't compile. And instead of compiling, it all of a sudden just went and said, hey, I'm done. This is what I mean by non-determinism. Okay, you've told the model to do something. It comes back and it lies to you. It tells you that it is done. Now, this is something that you will build in 101. You'll build this program right here. But this is talking to that model, and it's lying to it. That's why this is important. That's what I mean when I talk about deterministic workflows. You don't want to have, if this was all you were supposed to do, the model generated crap, you accepted it because the model told you we're done, it still doesn't even compile. This is the thing. This is why people say that models just generate crap. But what we talk about in 201 is how to make these workflows deterministic, how to not let it get away with doing this. Number one, how to manage context. I monitor context usage. When the context usage hits 55 or 60%, I basically hit the model in the head. I stop it. I prevent it from using more context, and I have it start all over again. And I just have it keep doing that until it gets it right. Now, it doesn't start all over again with no context. It already has some changes that were already on the disk. The next thing we have, back to the deterministic workflow, that was this other thing. And we talk about how to use Claude Code hooks. How do we use Claude Code hooks? How do we use shell scripts? How do we use drivers to actually inject determinism into our workflows so that this would never be able to, the fact of it saying that it was done would never be able to happen, because when that tool call ended, a hook would run, it would run the code and try to compile it and try to run the test, and it would basically come back and say, no, you can't stop, you're not allowed to, the test failed. And then it would just keep it working and keep it going and keep it doing that. The other thing that is probably important that I'm out of time, I just want to highlight this for the 201. It's one of the things that we talk about in depth is this concept of code reviews. I have code reviews done by 4 separate agents. Okay, one is it just has one is just a regular review. It says this directory contains C++ source code for tools related to trading. The subdirectory contains code for matching. See the readme.md therein. Review the source code and provide your feedback in feedback.md. Note, you do not have access to build tools. Do not build anything. Okay? It says just doing a regular code review. But this one here is API Audrey. It's a persona. And I would say that if you are doing reviews, I learned this back even before I learned about tool calling. Models behave differently when you give them personas. I have theories. I don't know why. Even new models. These reviews that I have right here were done on Sonnet 4.6, which is the most recent model that's been released, right? Sonnet 4.6. And these models, given these different directions, one by the person that I call Audrey. Audrey only reviews APIs. That's all Audrey reviews. Carl is concerned Carl. Basically, he's spent decades in, he's basically been working on at NASA and at nuclear power plants. I think even missile silos or whatever. Those are kind of his background. Nate is an old C++ guy, an old C guy from Bell Labs in the 70s. But I give them these things because this puts things in the context that allows the model to experiment. These reviews are very, very different. I even put a model to go and analyze all of the different reviews and how they work together. If you're doing C++, I think you really should have at least 4 separate review agents with different special tasks. None of them should be tasked with reviewing everything. Their focus is very small and confined. And then you can take another review agent that gathers them all together to figure out what code needs to be changed. These are things that I think are very valuable for going forward with evaluating the C++ code that gets generated.